All right, so today we're going to be covering gas stoichiometry. So what that means is we're basically combining what we learned from these past equations, the gas laws, and mixing it in with like grams and with limiting reactants. So we're combining this with a chemical equation. All right. So we're going to be doing three different types of problems. In the first one, we're going to be doing a molar volume problem. On the second one, we're going to be doing a decomposition problem. So you have a solid breaking apart into a gas, and we're gonna calculate how much gas we make. And finally, on the third problem, it is a limiting reactant problem where we don't even know the amounts of the gases. We just know their conditions. We know the pressure, the volume, and the temperature, and we're going to determine how much product we make from that. All right. So just stay tuned. It's going to be a little bit of a long video, but I'll try to make it short. Let's start off with the simpler problem. We're going to talk about something called molar volume, right? And that has to do with this little table right here. Very, very important table. This table is table 5.2 shows what you call your molar volume. And the molar volume is the volume of a gas when you have 1 mole of that gas. So if you have 1 mole of oxygen, it'll take up that volume, 22.397. 1 mole of nitrogen, 22.4. Hydrogen, etc. All the way to ammonia, that takes 22.07. So 1 mole of this is 22.079 liters. Now, notice that all of them are pretty much the same, with a few exceptions. And we'll explain those exceptions later on. There's no time for it right now. But what we really get from this information is that 1 mole of any gas at these temperatures and that pressure, it's going to equal 22.42 liters. And those conditions are what you call STP, standard temperature and pressure. So if you have 0 degrees Celsius and 1 atm, you can use this conversion to solve for things. So for example, in problem number 77, that's in our packet, but it is the first example on 5.4. This is page 180 something, 179 or something like that. 179 in the textbook. All right, so how do we do these types of problems? These problems are pretty simple. Let's read it. A sample of nitrogen has a volume of 1.75 liters. How many moles is that? So we have 1.75 liters of N2, and we want to turn it into moles. So using this equality over here, we know that 1 mole of N2, we're trying to find it so it goes on top, is equal to 22.42 liters of N2. And when you take a look at the units, the liters cancel, we're left with moles. So our answer is going to be moles of N2. And I believe after dividing that it's 7.8. Not I believe, I'm checking the book because I recorded this a while ago, but the audio was messed up, so now I'm getting lazy. 7.81 times 10 to the negative 2. All right, so that right there, that's it. Now, let's say if you had a different type of problem where it gave you moles and you had to go to liters, well, it would just be flipped. Like, let's just say you have 2.3 moles of N2 and you wanted to find the liters. Well, you know that 22.42 liters is 1 mole. So you can solve it that way. So you can flip it just like we did with dimensional analysis, just like we've done with unit conversions, all sorts of problems. It's the same concept. One goes at the top, one goes at the bottom, and that's it. Now, this one had 3 significant figures, so our answer should have 3 significant figures. All right, now that basically covers that first type of example. The next type of example takes it a little step further. we no longer talk about moles, but we start off with grams. All right, so let's check this out. So quicklime, calcium oxide is produced by the thermal decomposition of calcium carbonate. Calculate the volume of CO2 at STP. STP is a very, very important term, standard temperature and pressure. When you have STP, that means that 1 mole is equal to 22.42 liters. Keep that in mind because that might be useful. Whenever you see STP, you can use this. If it doesn't say STP, you cannot use it. No, no, no. All right, so no STP, no molar volume. But let's check this out. We have 152 grams of calcium carbonate. So 152 grams of calcium carbonate. Now let's think of a plan. We have grams of CaCO3, but you should never work with grams. You should always work with moles. So let's turn that into moles of CaCO3. Now, we don't want moles of CaCO3. We want volume of CO2. That's the ultimate goal. We want liters of CO2. So how do we get there? CO2. So, well, you can go from moles of CO3 to moles of CO2, and you can go from moles of CO2 to liters of CO2. All right, so we have a little bit of a plan. Let's go ahead and let's get started. So, we got grams of CaCO3, and someone was so kind to give us the molar mass of CaCO3. That was me. So 1 mole of CaCO3 is the same thing as 100.09 grams of CaCO3. Now, we're here. We got to keep going. We're done the first step. Check. Let's go on to the next one. Well, we don't want moles of CaCO3, so I'm going to put moles of CaCO3 at the bottom. How many moles? We don't know yet. But we want to go to moles of CO2. So moles of CO2 goes on the top. Whenever you have moles over moles, you have to look at the mole ratio. You have to look at the two things in your balanced chemical equation. Now this equation is balanced. I checked it earlier. You just got to count, right? 1 calcium, 1 calcium, 1 carbon, 1 carbon, 3 oxygens, 3 oxygens. Now, so that it's a 1-to-1 ratio. Makes our life easy-ish. But now we're at moles of CO2, and we got to go to liters. Well, we know that if it's at STP, 1 mole of CO2 will take up 22.42 liters. So we do a little bit of this math. A little bit. Just a tad bit. We got 152 grams. We divided by 100.09. We don't got to do anything with the ones. We multiply by 22.42. And we get 34.04. Whoa, Mr. Sanchez, 3 sig figs. What are you doing? You're making us all look bad. 34.0 liters of carbon dioxide. All right, so let's kind of break down what happened. In this problem, we had the grams of this substance, and we knew it produced CO2. So we figured out how much gas will be released simply by heating up calcium carbonate. All right, so we would release 34 liters worth of CO2. If you wanted to turn that into grams, you could, except you wouldn't use liters in this step. And that would just be like your regular old stoichiometry. So this is a very, very important reaction, or a very, very important concept. You can now tie in your masses with volumes of gases. All right, so this is a very, very important thing to understand, and it's a very important thing to practice. All right, but one important thing, STP. This only works at STP. Write that down somewhere, okay? Okay. And tell your friends about it. Whenever you see whenever one of your friends says, hey man, Did you know 1 mole is equal to 22.42 liters? You gotta tell them that's only at standard temperature and pressure, dog. All right. You know how you guys talk, whatever language lingo you guys use. No cap or whatever. I don't know what you guys say, man. All right, let's check this out. I wrote the ideal gas constant because it takes forever to write that out. So, all right. In this next type of problem, let's read it before writing anything down. Pretend I didn't write anything down. And I'm going to move this down in case my big old face is in the way. A sample of methane gas having a volume of 2.80 liters at 25 degrees Celsius and 1.6 atm. Oof. So whenever you see words like at and, those are unifying words. That means those three things go together. So all three of these things correspond to methane. It said, and it was mixed with oxygen gas having a volume of 35 liters, 31 degrees, and 1.25 atm. So those three things are for oxygen. The mixture was ignited to form carbon dioxide and water. Calculate the volume of CO2 formed at a pressure of 2.50 atm and that temperature. Oof. So, did it mention STP? No. So, we can't use molar volume. We can't say that 1 mole is 22.42 liters. We can't say that. So, we're not going to say that. But what we should do is we should write a chemical equation because it is stoichiometry and they did mention a chemical reaction. So methane is CH4. All right, and we said it's reacting with oxygen. Well, it's mixed with oxygen and then it's ignited to produce CO2 and H2O. And well, I won't write the states of matters right now. We'll write them later. Now, always balance your formulas. You see how there's 4 H's here? Well, there should be 4 H's on the right. So let's put a little 2 here to double this all up. That gave us 4 H's, which is good. But our O's, now we have 2 O's here, plus these 2, we have a total of 4. So we put a 2 here, so we have a total of 4 O's. All right, let's go on. They mentioned 2 gases. Well, they mentioned 3. They mentioned methane, they mentioned carbon dioxide, and then they mentioned O2. They gave us a list of information for methane. So over here where methane is at, on the left, we're going to make a list for methane, and on the right, we're going to make a list for, what was that other thing? Oxygen. All right, so let's make that same list that we have over here, but on the right hand side. All right, so the pressure for methane was 1.65 atm. The volume for that methane was 2.80 liters. The number of moles was unknown. And the temperature was 25 degrees Celsius, but if you add 273, that becomes 298 K. And then 31 degrees is 6 degrees higher. So we add 6 to that. So 2 plus 4, that equals 304 Kelvin. The number of moles, once again, is not given to us because they want to be jerks. They could have just gave it to us. The volume, 35.0 liters. And then the pressure, 1.25 atm. So they gave us everything but the moles. And whenever we're talking about balanced chemical equations, we need moles. So let's get rid of these variables and just simplify it and find moles. Because with moles, we can find information about other things. Remember, they want to find carbon dioxide. They want volume of CO2. So this is our goal. We want to go to CO2. We can't even talk about CO2 yet because we have no idea the number of moles of CH4 or the number of moles of O2. So we're going to do 2 problems using the ideal gas law to solve for moles. All right, so let's go ahead and do that. We're going to start off with CH4. So remember, the ideal gas law is P times V is equal to N R T. But I'm going to rearrange it so I can solve for N. So I'm going to divide both sides by RT, and basically our formula is N, and I'm going to put CH4 here, is equal to pressure times volume over R times T. And that's what we're going to use. But that T looks hideous, and I know you guys are going to bully me for that. There we go. All right. So let's go and let's plug things in. So we don't know the moles of CH4. That's why we wrote them out here. But we know the pressure. So 1.65 atm. We know the volume, 2.80 liters. We know R. At times I copy and paste. I love copying and pasting. It's like my favorite thing to do. But I don't know how to shrink it. Whatever. We'll put it in parentheses. And then the temperature was 298 K. All right. Now this is this looks hideous. This looks super hideous. Let me a little bit better, maybe, possibly. Whatever. Now N, the number of moles of CH4, we got to multiply the top and then divide by the bottom. So let's go ahead and do that. 1.65 times 2.8 divided by 0.080206. And then divided by 298. And that gives us our number of moles at 0.193 moles. So I'll write that over here in red. 0.19, 3 moles. And then I'll get rid of the little question mark because you're useless. We don't need you anymore. Now that's how you calculate the moles for CH4. We're going to do the exact same thing, but for oxygen. So bear with me once again. And now let's change CH4 to, We're going to change CH4 to O2. And we're going to plug in the values for that on the left side. Now, I'm going to move this a little up because it's, you know what? You guys are going to make fun of me for that line too. You're going to be like, Mr. Sanchez doesn't know how to write lines, even though there's a tool for it at the bottom. And then let's go ahead and let's write that over here. We got 1.25 atm. The volume is 35.0 liters. The R value, 0.0. Oh, I should have copied and pasted it. That's my favorite thing to do. No, come back, L. Here, take the L. All right. And then the temperature from oxygen was 304 Kelvin. So it's the same thing. Multiply the top, divide by the bottom. 1.25 times 35 divided by 0.08206. Hit equals, and then divide by 304. And we have that the number of moles of oxygen is equal to 1.75. So we don't need this little thing over here. We'll just write 1.75 moles. It's nice to be done with the problem, isn't it? Is what we're going to say in a couple of minutes. All right, we still got work to do. Let's look at what they asked for. It says calculate the volume of CO2. All right, we don't even have the moles of CO2. We actually have a little bit of an issue. We have moles of CH4, we have moles of O2, and we got to figure out the moles of CO2. So what we're going to do is two separate problems, and it becomes a limiting reactant type problem. So we have 0.193 moles of CH4, and we also have 1.75 moles of O2. And both of these have to be turned into moles of CO2. Where did that 1 come from, Mr. Sanchez? Imagine there's a little 1 in front of the CO2. So 1 mole of CO2 for every 1 mole of CH4. You don't have to write down the 1s. In fact, they look kind of ugly. I don't like them there. Whoa, what the hell is that for? I mean, what the heck is that for? Don't demonetize me, YouTube. I'm going to miss out on my 13 cents per year. People, if you want to see me make the big bucks, like, comment, and subscribe. No, just plain don't. Don't. All right. And we got to do the same conversion over here, right? We got moles of O2, but look, now for every 2 moles of O2, we make 1 mole of CO2. So we still write 1 mole of CO2 on the top, but underneath we put 2 moles of O2. And check it out. Multiply by the top, divide by the bottom. I'll do the top calculation. You guys do the bottom one. Yeah, this one's good. The other one, 1.75 divided by 2. I got something like 0.0. Wait, whoa. That's, I think I divided by like 800. I don't know why. 0.875 moles of CO2. And we always got to check. Did things cancel? This canceled, this canceled, this canceled, that canceled. All right. So with 1.75 moles of O2, you can make up to that amount. But CH4 with 0.193 moles, the most CO2 you can make is 0.193. So this ends up becoming the limiting reactant. So CH4 runs out first. So this stuff at the bottom, garbage. We don't need that. Let's erase it. Leave. What we use is that 0.193 moles of CO2 because the stuff at the bottom, was a little too much. That's the most we can make with that O2. But we run out of CH4. So we're almost there. Now we got 0.193 moles of CO2, and because I'm getting lazy and I want to throw away all the hard work I've been doing, I'm going to ignore what we said earlier. No, don't ignore it. Do it. No. Remember, we cannot use molar volume. We cannot use that 22.4 because it is not at STP. Unfortunately, what we got to do is, well, we got pressure, we got temperature, well, we got moles. So we are doing another type of ideal gas, or we're doing the same ideal gas law: pressure times volume times N times R times T. And we got the moles, so we're putting that on the right hand side. Uh-oh, what was that? So we got moles on the right hand side. We got R. And then we have the temperature. And the temperature is 125. 125. So we got the pressure and the temperature. Sorry for not making the list. I don't want this video to drag on because then you guys are going to be like, I don't like this guy. And I need the validation. All right, volume. Do we have volume? Volume. No, that's what we're looking for. Ay, Mr. Sanchez. Do you even think? All right, and then the temperature, I said that like a while ago and I never wrote it in. I'm going to scoot this over because we're running out of room. Well, actually, we can get rid of this. We don't need you anymore. We don't need you anymore. You're getting in the way. So pressure, volume, moles, R, and then the temperature was 125, but we got to add 273. And that makes it 398 Kelvin. Those of you that spaced out and are wondering where I got this from, I got it from here and here, and we calculated this together. Rewind and watch it. So how do we get V by itself? Divide both sides by 2.50 ATM. One thing I haven't asked for in these videos is for feedback. Keep it to yourself. No, I'm kidding. If you got anything good to say, let me hear it. If you don't have anything good to say, keep it to yourself. Make sure to like the video. Don't dislike it, because then it'll hurt my self-esteem. 0.193 times 0.08206 multiplied by 398 divided by 2.50 ATM, and the volume of CO2 is 2.52 liters. I gotta check that. I don't believe these lies. This don't seem right to me. It's probably right. Hold on, 0.193. I did it earlier and I got a different number. So let me just, I know something's a bit off. Divided by 2.50. 2.52 liters is what I get. All right, excellent. So that's how many liters of CO2 we made from this reaction. So it's pretty cool that you're able to not even have an amount of a gas or amount of any reactant, and you're able to figure out more complicated information. So that's just something to keep in mind on the importance of these. Now, the next thing we're going to talk about is not now because I think you're tired of listening to me, is the density, using the ideal gas law to find density. That's next, all right? Thank you for powering through all of this. Any feedback, please let me know. Peace out, people. Take it easy.